So usually when we think of robots, we think of humanoids talking in mechanical voices and moving in jerky fits and starts. This is a science fiction version of robots. Robotics is a field that carries this responsibility and promise like no other field in science, in part because it combines cutting edge of mechanics, machine learning, AI, and as we will find out today, material science. Do you know that Mars has 4 human-made robots on its surface? Mars 2, Mars 3 were physically tethered probes. Sojourner was dependent on the Mars Pathfinder base station for communication with Earth. Curiosity is on its own. This is an example of what our two guests are primarily devoting their work to: robots that are able to function in remote, unstructured environments. They had a super busy October, and we are fortunate to have them on the show. So, Professor Corina and Professor Genevieve at the Louisiana State University in Baton Rouge, welcome to the WhiteOwl Talk series, and thank you so much for taking the time off to talk to me.
Thank you for having us. We are
Thank you.
very excited.
So, Miss Corina and Miss Palardy, can you tell us a bit about your childhood, where you grew up, and your interests in high school?
Corina, you can go ahead first.
Sure. So I'm originally from Romania. I grew up like in a small town close to the capital, Bucharest, and I always liked mathematics. I was always interested in maths, physics, and informatics. So in Romania, we study informatics from high school. I really like that. So when it was time to apply to college, it was hard to decide what I wanted to do. But some of my friends were already studying like automation systems, and that seemed like a good idea. So that's how I ended up like doing robotics in general.
Yeah, in my case, I'm from Canada. I'm from the province of Quebec. I grew up in a village, a very small town. And well, similarly to Karina, I also really liked math and physics, mechanics specifically in high school. And but there's no specific reason why I ended up going to mechanical engineering. Just I knew it was a good field to use math and physics, and I also like computers, so it was a combination of all that. So that's why I chose to go into mechanical engineering as an undergrad.
So, did you
And
have an interest in robotics, or was it just maths which led you to robotics?
no, it was mostly because I'm in materials. So, robotics, I think everybody thinks it's cool, but I was more going towards materials, so lightweight materials that can be used in various applications. Robotics can be one, but I'm mostly in, aerospace and automotive systems for
Yeah.
lightweighting.
Yeah. So, from untethered to autonomous, it sounds a bit like life, doesn't it? So, Miss Corina, can you help us understand how the field of robotics has changed, and what is that the scientific community is working towards?
Sure. So robots started like actually a pretty long time ago. In the first time that the robot name appeared was in a Czech play, like drama play. And in Czech, robota means like forced labor. So that was the first appearance of the word robotics, and that was in the 1940s. So from there, like people started looking into robotics, and in the 70s, it was one of the biggest boom of robotics, where like you had a lot of the robotic manipulators started being used in the manufacturing industry, especially in car manufacturing. Like doing the tubes for old televisions, there were the first uses of robots. So the 70s, the 80s, very much focus on these robotic manipulators, and then starting slowly from the 90s was like a slow period for robotics in general, and then from early 2000 people started thinking, okay, robots working in more dynamic environments and more complex environments. So the remotely operated robots in general, they do have like a human that is going to command. If we talk about the type of robots that I work on, especially the underwater one, that means that you will have a cable connected to the robot and the communications go through the cable. But you want robots that are more self-aware and then autonomous and do not rely on human expertise. So then the autonomous robots started being the big thing in research from late 2000. So here, when we talk about autonomous robots, what we mean is like a robot that is able to act on its own in the environment without human input. So working in robotics, you have to, the human is still present because it has to create the robot. So it has to build the system, decide what materials to use, what sensors, what type of actuators, but then also develop the software, the artificial intelligence for the robots to be able to decide what they are going to do. So now with the boom of machine learning and artificial intelligence, like the biggest interest in robotics is how do we make these robots more robust and um, able to work in different type of environments. So if we think what we actually have today, we have a lot of robots in industrial factories that they work in precise movements, and they are able to do very well their job. Why? Because in this type of factory configurations, you have the robot that it's always doing exactly the same task with at exactly the same time. So there's no uncertainty there, you know. But in real world, where you want to have robots that work together with people, that's not the case. We as humans, we are very unpredictable. So you want your robots to be able to work with us without harming us. So that's where the challenge is now in robotics, and where a lot of people are focusing their attention towards.
Yeah. So one of the key areas of your research is control theory, which has its origin in the 19th century. So how does control theory remain at the heart of complex system design? And can you give some example of how it works in, say, cruise control or autonomous vehicles?
Sure. So control theory, it is the base. It's like basically the brain of your system. Without a control system, you can't have your robots do any type of movement, any type of action, right? You have, so the control system, it's basically taking all the information that it has about the robot and about the environment that it's working on, and then also considering basically the state of the robot, and tries to make decision based on that information. So as inputs, you would have like the sensor inputs, so the position, the velocities of your system. And as output, you can have another input. It's actually where you want to reach. If you imagine like a car, like an autonomous car, for example, you want to go from point A to point B. If you design a control system, then you know you want to reach at point B, and then you know all the time where your car is, right? So what you are doing, you are taking into account this difference between where your car is and where you want to reach, and decide, okay, how the car should move to reach to that point, what type of forces there should be applied to move the car. So again, without control systems and control theory, your car will not be able to move, because we decide what laws they need to be applied in order to move the car. So so control theory, it's not applied only for robotics. Every modern object in your house has some sort of control system. So it's a very important area of study and has high applicability.
Yeah. And path planning is the other leg of your research. Young robotics students find it challenging to build robots that move as per a map. How does path planning work at the bottom of the ocean?
So at the bottom of the ocean, it's a bit different because there the robots have a harder time to localize themselves, basically to know where they are, right? Because robots that work in the water, underwater especially, you do not have Wi-Fi, you do not have GPS. So you need other type of sensors to be able to estimate what's the location of your robot. But once you are able to put these more expensive type of sensors, you will be able to easily localize your robot in the environment. Now, once you know where your robot is, you start thinking, okay, now I need to navigate to this gigantic space to move around. So here, depending on the environmental conditions, sometimes depending on the capabilities of your vehicle, you will decide what is the best path to take. Also, depending on your application, if you want to study, for example, corals, and you want to look at corals at the bottom of the sea, what you would do, you say like you need to detect first, okay, where are these corals on the sea bottom, and then you will spend quite a large time designing like the paths that your robot should take underwater to gather as much data as you want in that area of corals. Now, path planning can be done in multiple ways. You can have, if you have already a map of the environment, a map of the sea where you are working on, in advance, you can predefine what is your path, what the path of your robot should take. But if you do not have that type of information, then your robot will have to have some sort of system that is deciding on the spot how the motion of your robot should change based on the, again, on the application and the environmental conditions that you are facing. Especially in underwater robots, especially they are autonomous, so they are not connected with a cable to the surface. They rely on their batteries that they have on board. So what you would want to do, you would want to make a motion of your robot that is not going to waste the batteries. You want something that is very energy efficient. And there's a lot of research looking at how can we move with the currents in the ocean so we can not fight against them, so that will save our energy so we can have longer missions.
Yeah. And another cool research area that you are working on is the use of artificial vision for biomedical application. The human body is better mapped than the ocean. So, what kind of uncertainties do you budget for in this application?
Um, so here, yes, that's true. The human body is much more well known than the deep of the ocean, but you still have uncertainty in terms of um, like the flow, the blood flow that is coming around, and especially in the area that I was focusing on a while ago, it was detecting tumors, different type of tumors for vocal cords. So in that kind of application, it's interesting because whenever you have a tumor, basically the blood that it's going around those tumors, they have like different patterns. It's not like your normal flow, but you can't say for sure, okay, it will always look like this. So the blood vessels, actually, they might be more, let's say, have like a higher curvature or be more thin. So it's a lot of uncertainty in that way when you want to estimate or you want to classify something as, is it a tumor? If it's a tumor, is it cancerous or it's not? So medical, or like especially like medical imaging, it's used for detection now and classifications of diseases. And why people want and research that is because you want to be less invasive. You don't want to do biopsies. If you could have like a vision system that would be able to tell you that information. So it's a different type of application.
Yeah. So you and Miss Palardy have collaborated on mobile manufacturing in uncertain scenarios. which demonstrate novel strategies for collaborative robotic systems performing post-processing operations remotely. So how common are these kind of collaborations, and how are collaborations such as yours important for pushing the envelope?
Um, okay, so I will start answering this.
Yeah, and I can add to this.
Yeah. So collaborations are really important in robotics and in manufacturing as well. I, as a roboticist, can't work by myself to come up with a solution for a problem if I do not have the information from material scientists telling me these are the problems. So basically, robotics comes as a tool to solve like larger problems. Collaborations are very important to advance the state of the art of research. Like nobody can work on its own. And in my opinion, this is essential to move the science forward. The project that we have, it's a National Science Foundation project, has been awarded at the beginning in fall this year, beginning of fall. So it's a very new project. And basically what it involves like a team of robots that need to work together with like some human operators that they perform finishing operation on large scale parts. So that means that you will have like a gigantic wind blade, and you don't want the people being exhausted by just polishing and trimming and sanding these type of blades. So you could use robots to do that. The problem with this is that robots do not know when the job is done. Like they don't have that information. So they would need some people there to tell them, okay, you finish the work, you are done. So what I can do as a roboticist, okay, I can say, okay, this is the robot, this is how they should work together. Where Genevieve comes in is like, okay, she tells me these are the properties of the material. This is how your robots should act. This is how the part looks when it's finished. So it's really, really important to have this type of collaboration. And I think Genevieve can add more about like the manufacturing, what we are trying to manufacture exactly.
Yeah, so on my end, it's basically the same thing. My expertise is in manufacturing of composite materials. So when I say composite materials, I mean fiber reinforced polymers. So you've probably heard about carbon fibers. So that's what we're talking about mostly, or glass fibers for wind turbine blades. And automation of manufacturing processes is a big field also for composite materials. So typically we will lay down layers of fiber reinforced polymers at different angles. So it needs to be controlled well. And if we need to manufacture large components, we ideally want to automate the process and use robotic systems to do so. So there are some processes like automated fiber placement, automated tape layup that are commonly used, especially in aerospace industry. But it's always pre-programming the robots or the robotic system in order to carry out the operations. So some issues that we see when we go through manufacturing of composite materials is that the initial parts that we plan for, so the initial dimensions, once the part is manufactured, it will not have exactly the same dimensions that you plan for. So for humans, it's not necessarily a problem. Like we can see what's happening with the actual geometry. But if we want to automate the process and make it easier for human workers, and safer overall by using mobile robots. So they need to be able to learn, okay, or to detect at least the final geometry of those large components. So yeah, and those are some of the issues. And one of the biggest one is to detect when the operations are completed. So For humans, it takes years. Well, not years, I'm making this up. I'm exaggerating, but it takes a while to learn, you know, to become an expert and learn, okay, this is when the operation is complete. So hopefully we can use some of that human expertise to help the robots learn when they complete their operation. So to make the process, you know, safer for